Hello, my name is Arthur Kay. I'm the Precision Analog Applications Engineering Manager, and I support products like op-amps, instrumentation amplifiers, references, and other linear products. Today we're going to discuss looking at datasheet specifications of noise and doing noise analysis to minimize the total overall noise. Let's take a look at a demo real quick. Here we have an amplifier connected up with a DC signal connected to the input, and the output should be a constant voltage, but we see a noise signal on it. That noise is not from external devices like power line or cell phones. This is noise generated by the circuit itself. We can use methods to minimize that noise. Let's take a look at some slides to discuss this. So this noise, as I mentioned, is intrinsic noise generated by the amplifier itself. This is a standard non-inverting amplifier, and each element, the op-amp and the resistors, generates noise. Over on the right-hand side is a noise model for that. We have a noise voltage source associated with each resistance. We have a noise voltage source associated with the op-amp and a noise current source associated with the op-amp. Let's take a closer look at the amplifier. The noise voltage source is actually analogous to an offset voltage. The noise current source is actually analogous to the bias current of the amplifier. In the data sheet, we're going to have a spectral density, and that's what is shown here. It's the frequency domain representation. On the horizontal axis, we have frequency. Vertical axis, we have volts in nanovolts per root hertz. We have nanovolts per root hertz, which is a density. We often have plots like this too. It's just an oscilloscope output plot or a time domain, but notice that it's limited from 0.1 to 10 hertz. So this is really only for looking at low frequency noise. So the spectral density has a low frequency region, and it has a broadband region as well. The time domain, I just want to emphasize that it's low frequency noise on the scope. The datasheet table is really generated from the spectral density plot. You can see it's just discrete points picked up from the plot, put in there. How do we take this spectral density and convert it to an overall output noise for our amplifier? Well, we can integrate over a given region. And that's what this formula is, a standard formula for integrating noise over a region. And the end result is an RMS voltage. By multiplying that RMS voltage by 6, we can get an estimate of the peak-to-peak. Noise is a Gaussian signal, so there is no true peak-to-peak. This estimate will be a 99.7% probability that the noise will be inside that range. But since it's a Gaussian signal and the tails of a Gaussian distribution go on forever, there's always a finite probability that a noise spike can go outside of that range. This is a good, commonly used estimate. Using that integration formula, we can actually do some simple hand calculations. There's many more formulas than what's being shown here, and some detailed information later shown in the references will give you other formulas that can be used. We're going to assume that this circuit is dominated by noise voltage source, and we're not going to even consider the noise of the resistances or the noise of the second stage. So here's the basic equation. We multiply the gain by the spectral density times the square root of the bandwidth. And if you look at this, the gain of the first stage is 100, the second stage is 10. From the data sheet, we have 4.5 nanovolts per root hertz, and the bandwidth is 251 kilohertz. And multiplying that all out, we get 2.25 millivolts RMS. The peak-to-peak can be estimated by multiplying by 6, and that's about 14 millivolts peak-to-peak. The thermal noise is noise from the resistors. This plot is a very handy plot to keep available when looking at or analyzing your circuit. Without a detailed analysis, you want to just compare the resistor noise to your op-amp noise. So for example, if you're using a special amplifier that has very low noise, let's say 1 nanovolt per root hertz, and you're using that with a 10 kilo ohm resistor in the feedback, you can get 10 nanovolts per root hertz from the resistor and 1 from your amplifier. Thus, the resistor noise would be dominant. Normally in low noise circuits, you want to make sure that the amplifier noise is dominant. So this is a very good, simple way of just seeing what your resistor noise component would be. Finally, how do we reduce the overall noise for an amplifier? First, we need to just select a low noise amplifier. And you can do that by looking at the datasheet characteristics we discussed. We should look at both current and voltage noise. We haven't really talked about current very much in this. Current is most important when the impedance on the input is quite high or the feedback impedances are quite high, and that current is turned into a voltage noise. The references that we see later will talk about that in greater detail. We also need to consider both the low and high frequency noise, the 1/f region and the broadband region. This is especially important on wideband amplifiers. For low bandwidth amplifiers, it may not be necessary. Also, we need to make sure that the feedback resistors are appropriate, and low resistance will translate to low noise. And finally, we should limit the bandwidth to the minimum bandwidth that is required for our application, because wider bandwidth always translates to more noise. Let's do a simulation. We can actually simulate the circuit that we have in our demo here, and it's very simple to do this. We just say analysis, noise analysis, and it has an output noise and a total noise checkbox. Check them both. The output noise will give us the spectral density. The total noise will give us the integrated noise. Set your frequency range to the appropriate range for the bandwidth of your application, a little beyond the normal bandwidth, usually a factor of 10. We get the spectral density plot first, the 1/f region, the broadband region, and then the amplifier's gain bandwidth rolls off the noise. Finally, we get a total noise that's being integrated and converges to a value of about 2.47 millivolts RMS. And so that's the final total noise when the integration is complete. If we look over here, I have just listed the calculated, measured, and simulated results. And you can see they all compare quite well. The calculated is a little low, but remember, in the case of the calculated noise, the resistor noise and output stage noise was not included. So the simulation will include the effects of the current noise, the voltage noise, and all the resistor noise. It's going to be more accurate. So let's go back to our demo real quick. Again, here's the output of the circuit. If you look closely at the bottom here, it shows that we have about 2.7 millivolts RMS of noise. Many oscilloscopes have a noise feature measurement for RMS, and you can also see the peak-to-peak value is appropriate with the multiply by 6 factor. Our circuit is inside this shielded environment, which is a can that could be purchased at any, paint can that could be purchased at any hardware store. It's a very simple and effective shield, and we're just connecting our output and power supplies to the board as shown. So in summary, noise can be calculated, simulated, and measured. And hopefully all three results are equal to each other. If not, you need to determine the reason why they're not. And this presentation should help you to understand how to look at the data sheet and simulate, measure, and calculate the results to minimize the overall noise. Please look at the attached links for additional information. Thank you for your time.